So you see, so in the last lecture we talked about essentially we are currently talking about file system implementation, and now we are talking about the allocation methods. We talked about contiguous allocation and the external fragmentation problem that it poses, and then we talked about the linked allocation, right? However, in the linked allocation, we saw that linked allocation, while it solves the external fragmentation problem and size declaration problems, because you are just creating external fragmentation problem is solved and both are solved simply because you are just creating a linked list of blocks, right? Um, However, it's slow. In the absence of this FAT, the table, this linked allocation cannot support efficient direct access. And what is the trade-off for FAT? Well, you need to keep that FAT table somewhere, right? And I think we gave this example or exercise yesterday. 512 GB hard disk, each block size 4 kilobyte. Then the FAT table size is around, if you do the math, you will see that for having the addresses of the indices, the FAT table size would be around 432 MB. Each pointer size is 4 byte. You should assume that. But the thing is that if you have 512 GB hard disk, you have a medium sized or mediumly powered laptop. You might have terabytes of memory. What would you do? Or terabytes of storage. What would you do? The fat will just grow. Right? However, without fat, this linked allocation cannot support efficient direct access. Right? So to solve this problem, essentially we have the last method called indexed allocation. Indexed allocation solves this whole problem of fat or whole problem linked allocation of you don't really know where the blocks are and there is no direct access because you need to always follow the pointer to the next block. This is solved in index allocation by bringing all the pointers together in the index block. Each file has its own index block, which is an array of disk block addresses. Again, remember that what is disk block? Essentially, it's basically 0 to dot 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 n physical blocks. This ith entry in the index block. Okay. So the ith is there a question? No, reacted, I guess. Okay, good. So the ith entry, like any entry in this index block, points to the ith physical block of the file. That actually means if you want to do 75th byte of a file, essentially you can just traverse this index block and access the actual file block. Now, what does it mean? That when the file is created, all pointers in the index block are set to nil because the file has size 0, no data blocks are accessed. When the ith block is first written, then a block is obtained from the free blocks and the pointer is adjusted. Okay. So to find and read the ith block in this scheme, you just traverse this index block and then you know exactly where to from where which physical data blocks on the disk do we need to read or write. This is the basic idea of indexed file system. So in the indexed allocation system, let's give an idea here. So that this directory structure here we consider in this directory, there is one file called zip and the index block is 19. So what is in this 19th block in this on this cylinder is basically your hard disk, because in hard disk is basically as like your HDD, basically hard disk drive is basically cylinder, and this your 19th block that is called your index block. What does the index block have? It basically has that where the rest of the data is. The first data is in ninth block. Second data is in 16th. Second block is in 16th. Then first block, then 10th block, then 25th block. And what is -1? These blocks, this index block pointers are not yet allocated. all of them are allocated. Okay? So what is the size of the file? If we have a 512 byte blocks, the size of the file is 1, 2, 3, 4, 5. So 5 into 512. Simple. So essentially in the index block, you have a separate data structure to make the direct access possible and fast. That's it. And where is the index block stored? Well, it is stored in another block, like physical block on the secondary storage on a hard drive. And only that index block's address is stored in the directory structure. Now, to give you a perspective, what did we start with? A directory is basically file name and then the data block, the pointers to those data blocks. From there, for the sake of efficiency and performance, we came up with this idea of index block. Now, moving into this indexed allocation, let's look into a little bit more, simply because indexed allocation is extremely popular and it's in use in almost all the operating systems that you use, like NTFS, your RazorFS, Journal System, ext2, almost everywhere. So indexed allocation combines all the indices, right, for accessing each file into a common block, right? I mean, this index block. So essentially, you need an index table for that. And but once you have that index table, you can do random access. And while doing this random access, you don't need the contiguous allocation. Which means that this does not have the external fragmentation problem that is generally there in contiguous allocation. But you need to get the space for index block from somewhere. Nothing comes from free. So essentially, this is more. This becomes, I would say that becomes problematic when you have only small files, because you created index block, say with 10 pointers, and you say like, in most of the file system, you have a maximum file size. You should know this, because if you want to create a 1 terabyte file, it will possibly fail. In older file systems, currently it is, I think, 64 terabyte or something. But the whole point is that for this size constraint on a file comes from the size of the index block, because in index block, right, each 4 byte pointer points to a data block. So you have a constant number of 4 byte pointers that you can accommodate. So you have a highest size of the file. The number of data blocks an index block can show. Now, if you have a very small file, lots of very small files, like 1 byte or 1 or 2 blocks in size, that means most of the space for this index blocks for the file goes to waste. Now, to give you an example why that is a problem, in the linked allocation, we will lose only the space of 1 pointer per block. We don't lose a whole block as this index block. So how to solve this problem? Like, you give the index table at the beginning to a file, but the file might not be able to use it. So how to solve that problem? There are a couple of variants. There are some couple of variants of indexed allocation, and we'll come to them in due time. What I want you to understand is that this is systems development. And in systems development, everything has goods and bads. And more often than not, the solution is to take for each of the methods the good and remove the bad from it, or something coming out, something hybrid. That's why systems research, development, building is so close to engineering. We'll come in those hybrid schemes in due time. Give me a couple of slides. But let's actually see that, assume that you are using indexed allocation, because now we are understanding the basic ingredients, the contiguous allocation, linked allocation, and now the indexed allocation of the blocks to a file. So essentially, the mapping from this, if you assume that in the operating system, a file can have a maximum size of 256K bytes and block size of 512 bytes. Then essentially, so what is the maximum size of the index table? See, the maximum size of the file is 256 kilobyte and each block is 512 bytes. So there can be how many pointers can be to these blocks in an index block? If you actually do the math, it will come up to at most 512 blocks. So what does 512 blocks means? Meaning that we have essentially 512 entries in the index table. So this is the maximum size, this is the block size. You calculate the 256K divided by 512 bytes, you create the maximum block size by a file for a file. So maximum block size of the file is 512 blocks. That means we need at most 512 entries in the index file. Now, if we assume there is like a 1 byte pointer, then 500, we need 512 blocks. So basically 1 block for this index table. The size of the index table is 512 bytes, and then you can know how many blocks we need. It's 1 byte. So in this case, specifically in this case, where you need only 1 block for index file, Q and R are the quotient here is the reminder. When we divide the logical address is that I want to read 110th byte in a file. So when we divide the logical address by the block size, which is 512, and Q is the block number, is essentially a displacement in the index table. Right? So in Q, that actually means that LA by 512, meaning that you need to go this much in the index table, and then you want to go the remainder into the block itself. So this will go give you the index table pointer, index table, the position in the index table, displacement in the index table. And when you go to that byte of the index table, you follow the pointer, go to the data block, and then do the displacement within that data block. What does it mean? Say if you're going for 500, so you want to read the 75th byte. If it is a 75th byte, that means that it is in the first block, because each block is 512 bytes. So each block will be like not each block, I'm sorry, each byte in the index table will point to a 512 byte pointer. So what is the displacement within the index file? 75 double division by integer division by 512, which is 0. So you will go to the 0th pointer, the 0th location in the index table, and following that pointer you go to a data block, and within that you will go to 75th byte and start reading or writing. Any questions so far in the indexed allocation? So you have an index table, and the index table points to data blocks. So if I give you a logical address, first you will find the displacement into index table, and then follow the pointer, go to the data block, and then displace into, and basically you do the displacement into the block. Any questions so far on the indexed allocation and using the indexed allocation in a file system? Okay. So now we need to implement the index table, right? Because the index allocation has your additional overhead of having one index table per file. So to implement the index table, we need to answer a basic question. How large the index block should be? Because each file must have an index block. So we want the index blocks to be as small as possible. However, if the index block is too small, then it will not be able to hold enough pointer for a large file. And you need to have yet another mechanism to have a multi-block index file. Understand this. So first we talked about contiguous allocation, linked allocation, or indexed allocation. The indexed allocation is sort of the best of both worlds. Like it's fast, it gives direct access, and really don't need to worry about external fragmentations. However, in indexed allocation, you need to implement the index table. And for index table, because you need to implement it, no one is going to tell you that what the size of index table should be. If it is too big, then you are wasting space. If it is too small, if it is too big, then you are wasting space, because each file will have to have an index table. Extremely hard, because lot of space will just go away, because you need an index table, store an index table on the disk. On the other hand, if it is too small, then you need to have multiple block index table, or you need to constrain the size of the file too much, which is problematic. So to that end, there are three variants of the indexed allocation to create the index table. So the first one is the linked scheme. So what is a linked scheme? Here, an index block is just one disk block, which can be read and written in a single disk operation. Index block, one block, essentially. And the essentially the first, this is creating it as disk block. Then if you necessary, so if it is necessary, meaning like as the size of the file increases, you need more indices to point to more data blocks, then you add a pointer to the end of another new index block. Start with one block, then you just added links to the next index blocks as and when needed. What does it mean? It means that the index table can be infinite in size, or at least not infinite, but rather it can actually take the all free space in a hard drive. So essentially, theoretical, there is no limit on size in this indexed indexed allocation linked scheme. Okay, so essentially, the linked scheme is, I would even say that this is a hybrid again, the hybrid that I was talking about. It's a hybrid of indexed allocation and linked allocation. The difference is that the linked allocation only used on the index table. So this is our first scheme, that is the linked scheme. Now, a variant of this linked representation uses a first level index block to point to a list of second level index block, which in turn point to a third blocks. So you have one index block, and in the original indexed allocation, entries in that index block are basically pointers. And those pointers point to data blocks in the original implementation of indexed allocation. But here, there is a first level index block, the original index block. And it points to a second level index block. And if you have the level equal to 2, which is generally the case, then second level index block points to data blocks. If level equal to 3 in this multi-level index, that means that the second level index points to more index blocks. So it will essentially, even if you start with one disk block, the number of final data blocks will increase exponentially with the levels. It's like a tree. You start with one index block, it will point to multiple other index blocks. They might point to other index blocks, and finally at the leaf, you will get some data blocks. Now, this approach can be continued to a generally third or fourth level, and depending on the desired maximum file size. So let's see what is the maximum file size with an example. Now, let's say what is the maximum file size for a two-level index in a particular setup of an OS. Assume there is a 4 kilobyte block size and 4 byte pointer size. Then the first index table, there's a two-level index. The first index table will have a 4 kilobyte divided by 4 byte number of pointers, which is like 2 to the power 10 pointers. And each of these pointers point to another table, another index table. Okay, and this essentially contain the total number of entries in all second level tables is that 2 power 10 multiplied by 2 power 10, and each entry in this 2 power 10 into 2 power 20 total entries point to a 4 kilobyte block. So maximum file size is 2 power 10 which comes from 2 power 10 pointers, and each one of them can address 2 power 10 in data blocks, and each data block is 4 kilobyte of size. So maximum file size is 4 GB. Okay. Now there are two essentially take-home exercises with this example. So if you do, so before we do that, do you understand this part in multi-level index? If you have any question, please write. Okay. So the best way of testing that whether you understood it is to possibly, do some exercises. So write down this exercise. Essentially, what would be, and I put the answers here. If you cannot do that, please ask on MS Teams anyway. But this should be, but if you can do that, you know that you understood multi-level index. The first question is the generalized expression for maximum file size when we have n-level index, 4M byte blocks and 4 byte pointers. For n-level index, not here is n equal to 2, with a 4M byte block sizes and 4 byte pointer sizes. Okay. So the answer is 4 multiplied n to the power n plus 1, but see whether that is actually, whether you can actually come to this expression. The second exercise is, what would be the mapping for this scheme from logical addresses for a particular file? Like access the lth byte to a physical block address when block size of 512 bytes and pointer size of 4 bytes. And I put a hint here because we want you to give an algorithm that you need to first find the block number in the second index table, and then you have to go from there. So you just we want to actually access this 928 byte of a file, a random number, some number. So how do you translate that logical address of 928 to this block numbers, like what indices in the first block, one is first index table, what is in the second level index table, and finally what is the displacement into the data block itself. If you can do these two exercises, then you know that you understood multi-level index, which is not hard to understand perhaps, but extremely easy, it's not easy, extremely, I would say, useful and actually use. Like if we have done the PintoOS file system implementation, you would have seen that you need to implement multi-level index for indexed allocation. So to wrap it up, here is like a schematic of this index allocation with multi-level index. So essentially, we need a whole index table for accessing the data blocks assigned to a file. So you start with the first block, right? First level, like you want to actually, so this is the directory structure. It basically talks about, here is my index block. This is the first outer index block, and this index block points to multiple index tables. So each one of the pointers point to multiple index tables, and each entry of this index table points to data blocks. So is there any question so far? If not, then I'll ask you a question. What is the problem with index blocks? As I told, everything has a trade-off. Contiguous allocation has external fragmentation, link allocation has performance penalty. So what is the trade-off for index block? Aside from that, you need to store the index tables, because now we have this multi-level index tables, which sort of like reduce the space. So for the multi-level index and indexed allocation, what is the trade-off? What is the problem? Can you think of any problem here? Anyone? More memory accesses. Okay. Number of accesses will increase and each level will need to be checked. Okay. Accesses increase. Okay. Yes. But so I would agree with Ayu, this succinct, like more memory accesses. Yes, absolutely. You need to access more. It's not memory, by the way, it's more like more disk accesses. But yes, you need to actually access multiple blocks and you need to follow these indirections. Okay, this is like levels of, you can call it like levels of indirections. Start from the directory, go to the outer index, then you go to the index table, then you go to the data block. Before you just start with this before it is you start with the directory entry and you just go to the index block, then you directly go to the data blocks. So essentially this number of disk accesses, right, they increase with index blocks. And now we need to understand this happens for every single read or write. So numbers add up very, very quickly. So the question here from a system developer's point of view is that, so how many levels do we have? Because levels actually control the number of indirections. So here's the thing that is worked in Unix, that has worked for a long time. Okay? They have this hybrid approach. And always remember, if you're going into systems, a hybrid approach is the best one. It just depends on which approaches do you want to put into your hybrid. So it's the idea is that, so you have this whole FCB, like file control block, which we talked a lot about. And we talked that file control block is basically the metadata, that everything or the metadata that you need except for the file data itself. But even the data pointer to the file data is in file control block. So what happens is that in Unix and in extension in Linux or the basic Linux, you have, say, first direct blocks with 15 pointers to direct data blocks. And then you have a single indirect, meaning that one data block will pointer to a data block, which will have this index table, which will have this data blocks. And then you have a double indirect. And then you have a triple indirect. What does indirect here mean? It just means that you point to these different index tables, and each index table will have pointers to, like each entry in the index table have pointer to these data blocks. So essentially, how does it work? The data for the small files, for example, of no more than say 12 blocks, right? Or 15 blocks, like whatever the direct blocks, they will be directly stored here. This will handle the small files. This will handle the medium files, the single indirect. And when you are getting like two huge files, which is anyways problematic to handle, as you might know, at least the ones that deals with gaming might know, right? Uh, Essentially, they actually be used, the single indirect blocks will be used for your index tables, multiple level index tables. So total, you have these direct blocks, and then you have this single indirect pointed to this one index table, pointed to an index of index tables, and then you have triple indirect that have not shown because it will take too much space, but you get the idea perhaps. It's like pointed to an index table. Each entry of the index table points to other index tables. Each entry of that other index table points to a data. Similarly, triple index will be, triple indirect will be. Now, using this methods, the number of blocks that can be allocated to a file exceeds the amount of space addressable by a 4-byte file pointers used by many operating systems. So essentially, for example, a 32-bit file pointer reaches only by 2 to the power 32 bytes or 4 GB. And for that reason, many Unix implementations, like including Solaris and even Mac, they now support up to 64-bit file pointers. Now I am leaving you again with a question. So the essentially so far this is like combined practical real world scheme that is used in Unix. So my question is that what is the total max size of a file? If you have total say n, if you have total say n blocks addressed to n blocks here, so there is like 3 would be stored for going for multiple levels of index tables. So you have this n minus 3 direct blocks. Okay. So this is the exercise for you to know if there are n such blocks like the indirect, single indirect, double indirect, triple indirect plus double direct blocks. Total you can have n. Then what is the maximum file size that you can support using this? Okay. But the I mean, just a hint is that for direct blocks is basically linear. Single indirect, it's basically like it will be again linearly. It's basically multiplied by n. Double indirect multiplied by n squared. Triple indirect multiplied by n cube. Now we talked about 3 types of allocation, right? Contiguous, linked, indexed. Indexed is used a lot. So for we actually talked about how to store the index table, how to make it better. Okay. So how to choose the which allocation of disk blocks to file system do we want for our file systems? We often find it using the performance of these allocation methods. Like for example, which one works best? Okay, and that is the performance. And essentially the question then boils down to how do you measure performance of contiguous and linked and indexed allocation? Because you need to mathematically measure it, then you have to run experiments and you need to get numbers that which one works better and which one works worse. So the best methods often depends on the file access type because the contiguous is great for sequential access and random access both. Because for any type of access, contiguous access requires only one access to get a first disk block, and then it can read in bulk the whole contiguous disks. We generally in contiguous access keep the first address of the block and then the size of the block. So total how many blocks to read after that block. For a linked allocation, we can also keep this address of the next blocks in memory and read it directly. This method is fine for sequential access. However, for direct access, like if you want to do random access in a linked list, like linked allocation, it becomes a problem. Because an access to the ith block might require I disk reads. You're reading I like basically require reading each and every block in the link. So this problem indicates that why linked allocation should not be used for an application which might require direct access. So that's why some systems, as you can see, like this, if you have, so contiguous is great for sequential and random, but we know that contiguous is bad for external fragmentation. Linked doesn't have external fragmentation, a linked list, but I know that, I mean, remember this always, like an array is very good for random and sequential both. Linked list is good for sequential, bad for random. You need other methods for random access in linked list. So some systems actually take a small route, it's easy route. They support both direct access files, which will use contiguous allocation, and this is sequential access file by using linked allocation. But how do you know that what is, or you as the operating system developer, how do you know which one is direct access files and which one is contiguous or which one is sequential access files? The type of access needs to be made at creation. It needs to be declared by the user. And they need to select either contiguous or linked. Okay. Now, indexed allocation is more complicated. If the index block is already cached into memory, then the access can be made directly. However, keeping the index block into memory requires space and sometimes considerable space. And if this memory space is not available, then for a single indexing, we need to read two blocks. One, first read the index block and then read the actual data block, which means twice more performance penalty. So that's why some systems actually combine the contiguous allocation of blocks with indexed allocation. By using this contiguous allocation for small files like you show in Unix, and then switch to an indexed allocation if the file size becomes larger. Since in the operating system, most files are small, like if you look into the file sizes, most of them are small binaries. And those binaries, if it actually reaches like 1 MB, it's actually pretty huge, essentially. So essentially, you have a hybrid where you use contiguous for small files, like contiguous memory allocation, and that indexed memory allocation as the file size grows up. So using performance, you can actually decide whether you want to use contiguous or whether you want to do linked. And in indexed, often you use a mix of contiguous and index, a hybrid. Since disk space is limited, you see, like we are talking about so far, we assume that there is a free space pools from somewhere, and if you ask the operating system, they will just automatically give you all these free spaces, and you add it to your heart's desire to a file. Well, you need to do the index table and all this pointer manipulation to first have a table to index, first have an index table, which will again point to index table, which will again point to index table, which will again point to blocks and so on, all those nice things. But you assumed that you can get a block whenever you want. Aside from contiguous allocation, you never had to think about you cannot get a block. And even in contiguous allocation, the problem that you had was that, yeah, I have free blocks, but they are just not contiguous blocks. However, you need to know as an operating system how much free space, how many free blocks do you have. And for that, essentially, we need to keep a tab on how much space is used, how much space is limited, how much space is reused, and so on. Okay, and for that, any operating system maintains a free space list. That's how you would know, you actually know that how much space is left in your C drive, in your D drive, in your you can actually do some commands like in Linux, you can write df -h. It will exactly tell you that how much data, how much space is left. And this free space list records all the free disk blocks. That is, those are not allocated to any file or directory. So we will use the term blocks here for simplicity, but often say in in the operating system, they generally consider clusters of blocks or groups of blocks for ease of maintaining this free space list. Free space list is nothing but whatever is not used now. Whenever you are giving, or basically operating system tells that a free space is given to a file, it marks that it removes it from the free space list. So to create a file, what happens is that the operating system searches the free space list for the required amount of space and allocate those number of blocks to the new file. Quite frequently, this free space list is implemented as a bitmap or bit vector, where each block is represented by one bit. If the block is free, the bit is 1. If the block is allocated to a file, the bit is 0. The main advantage of this bitmap approach is that its simplicity. It's just 1 bit per block. And its efficiency in finding the first free block of n consecutive free blocks on the disk. In fact, many computers supply this bit manipulation instructions that can be used effectively on bit vectors. That's why people use this bit vector list, because ultimately you need to know that I want k free blocks, how to get k once in this bit vector. One technique for finding free space is to sequentially check each of them, go sequentially and then basically say this is free, give them, this is free, give them. So essentially, meaning the first non-zero word is scanned for the first 1 bit, because it is 0 or 1. So you scan, you get the 1 bit, and which is the location of the first free block. Then the block number of that first free block will be the index of the first 1 bit. So if we calculate the value of the index, it will be like number of bits per word and number of zero value words and offset of first 1 bit, like offset of the first where you get the 1 bit. The cool part is that essentially this is just a scanning and finding the first bit, which means the first block which is free. And the cool part is that CPUs has instructions already to return offset within a word of first 1 bit. So essentially you divide this bit vector into words, and then you will get the first 1 bit in that word by one single instruction. So when you get the first 1 bit, like if you are going subsequent bits, you can calculate their block number by just doing an arithmetic manipulation, where you have number of bits per word, like how many bits did you see so far, plus number of zero value words, multiplied by number of zero valued words, because those are already occupied. Zero means occupied, and essentially 1 means not occupied. So now you know that, okay, actually step back. I actually assume that it might, so just to clarify, when you are saying words, that actually means that in computer, like in CPUs, have instructions to return offset within a word and not within the first, like the total size, because it might be arbitrary sized. So it basically divides them into words, chunks of data. And CPUs have instructions to return to actually do direct manipulation of words. What does it mean? Meaning that in each word, if you just call like give me the first 1 bit, either it will give you the index or it will fail. So you can go word by word scanning, and you can keep a tab accordingly that, well, the first word doesn't have any 1. Okay, so the block is the number of bits per word, whatever the word you set, and the number of zero value words. So total, how many bits have you seen, which is 0, plus how many bits that you have seen, which is 0, and then offset of the first 1 bit within a word. All of this can be done using CPU instructions, so extremely fast. Unfortunately, even after doing all these juggleries of words using the special instructions to find the first 1 bit, like first bit which is value 1 and not 0 in operating system, it is still, the bit vector is still inefficient due to space, not due to time. Because bit vectors are inefficient unless the entire vector needs to be kept into main memory to push it to CPU, right? So it means that in main memory, it is possible, like main memory needs to have space for this bit vector to know which spaces are free. And it is possible for smaller file systems, smaller disk size, but and not for large ones. For example, if the block size is 4 kilobyte, which is like 212 bytes, and the disk size is 1 terabyte or like 240 bytes, as I wrote here. So then the number of blocks, or n, is simply like 200 out of this 240 bytes. How many blocks are there? 240 by 212 to the power 40 by 2 to the power 12, which is like 2 power 28, right? So thus the number of bits we need is 2 power 28 bits, which is like 32 megabyte. So if we consider effectively clusters of 4 blocks, right? Then 4 blocks each, then we need 1/4 byte to find free space. So essentially, we need at least 8 MB of memory always given to this bit vector. So remember why clusters? Because remember in a bit, I mentioned that simplicity, I'm talking about this blocks, like each bit one block, but each bit can have 4 blocks for reducing the number of bit vectors. So it is 8 MB for like this disk size of 1 terabyte block size. This is okay, but you need to actually essentially, if you want to make your hard drive say 1 petabyte, your memory has to be increased tremendously just due to just because you increase the disk size. Think about it. Today, this is not the case. You can add as much disk as you want, as much your motherboard supports, and you don't need to worry about RAMs. In fact, after 16 GB or 32 GB, to the RAM is not that much needed if you are not running too much a rig, a cryptocurrency rig or something. However, if you use this method, it means that you when you buy hard drive, please also buy some RAM. That is just not good, right? However, this definitely gives a feel for this. It is easy to get contiguous files because you just, if once first you need to actually give a bit, like in a bit vector, if you get one, then you can just scan till you get the first one. So it's basically you are going to check the maximal substring in a bit string, which has all ones. And there are efficient algorithms for that. That's an algorithm problem. So there is another approach of free space management, which is that aside from bit vector, which is basically using linked list. So you link together all the free blocks, disk blocks, keeping a pointer to the first free block in a special location on the disk and caching it into memory. And this first block that contains a pointer to the next free disk block and so on. So you start with the first one, then the second one, third one, and so on. And basically you adjust, you basically adjust whenever you are assigning the first 3 blocks. So you adjust the first free space list somewhere here. So you have I want 3 blocks for my file as an application. So your ways will look into, well, 2 first will go to 2, then 3, then 4, and then I'll just give it to the application, or your operating system will give it to me, and it will adjust the free space list head to 5. That's it. It's just pointer manipulation. There is no waste of space, unlike bit vector, which basically told you that if you buy more hard drive, please also buy some more RAM. There is no such waste of space. Okay. Now, there is also no need to keep another table in memory. However, the problem with all linked list is expensive to traverse the list. Linked list, traversing the list is expensive. And for searching and doing all these things, you need to do that. And another problem is that we cannot easily get contiguous space for a contiguous allocation easily if we use this free space list. I mean, more specifically, it is not efficient to traverse the list. We must reach each block, which requires substantial in I/O time. However, traversing this free list is not a frequent action. Usually, the operating system simply needs a free block so that it can allocate that block to a file. It doesn't need 4 blocks, like give me 20 blocks, because even the operating system, like when you are writing data to a file in your code, like the operating system doesn't really know that you're going to write 2 GB more data. It just like, give me another block, give me another block, give me another block. So you don't need to traverse the file. And the most common operation for linked free space list is that you just manipulate the first, the list head pointer. That's it. So even after this Basel file system algorithms that we learned, we have this disk abstraction, we talked about this whole file system directory, talked about contiguous allocation, linked allocation, indexed allocation, and we talked like, for these blocks, we need this free space management and all these things. There are still things that we can use to improve performance in several ways. For example, some systems maintain, like many systems actually maintain a separate section of main memory as a cache where the blocks which are used most, they are kept under the, or used most recently, they are kept on the assumption they will be used again very shortly, very quickly. In fact, other systems cache file data using a page cache. This page cache uses virtual memory techniques to cache the file data as pages rather than file system oriented blocks. So implementation wise, file system had blocks, main memory has pages. But today, many systems actually cache the recent most read file data in pages. And simply because this page algorithms, paging systems are extremely efficient, extremely well developed, that actually make the file operations faster also. So this buffer cache that we talked about, oftentimes this is used using virtual memory page cache. Memory and file system goes hand in hand, some sense in caching. Another issue that can affect the performance of I/O is whether writes to your file system occurs synchronously or asynchronously. What is synchronous and asynchronous? Synchronous writes basically occur in the order in which the disk subsystem or this basically receives them, and the writes are not buffered. Thus, the calling routine must wait for the data to reach the disk and then write one after another. On the other hand, in asynchronous write, the data are stored in the cache and control returns to the caller. So you told that that is what happens, the asynchronous read. Because I don't know about you, but I have seen when my computer is too loaded, if I try to create a file, like using a command like touch, or if I want to redirect this data, it appears after 5-second lag. Because the writes to disk are often asynchronous. And these asynchronous writes are done the majority of the time. However, metadata writes can be synchronous because metadata writes are small, it is not huge data write, and it absolutely needs to be in order. So operating system frequently include a flag in the open system call to tell that whether they want the write to be synchronous and asynchronous. For a synchronous write, it is slower, but it will preserve the order in which data is written, which is sometimes important, specifically for metadata when you are updating the size of a file. On the other hand, disk write for just putting the data blocks can be asynchronous, and it is much faster. So some systems actually even, so this is this is yet another, so this is a bunch of optimization that we are talking about here. You should always think about using buffers, and you should always look for asynchronous writes wherever possible and synchronous writes whenever necessary. Necessary means that you need to write something in order, like just write after one after another. And this generally is useful when you want to update a particular variable. That generally has to be synchronous. Now, some systems optimize their page cache by using different replacement algorithm depending on the access type of the file. Recall that page cache is also used for caching file blocks. And this sequential access can be optimized by techniques known as free behind and read ahead. Free behind removes a page from the buffer as soon as the next page is requested. The meaning freeing whatever is done. The previous pages are because the previous pages are not likely to be used again and waste buffer space, so you just remove them. With read ahead, a requested page and several subsequent pages are read and cached, and these pages are likely to be requested after the current page is processed. Retrieving this data from the disk in one transfer, basically, and caching them saves a considerable amount of time. So essentially, you just read ahead the next pages. You free behind once a requested page, as soon as the next page is requested, you basically say, I don't need the previous page to free buffer space. So you free behind essentially means you basically remove buffer space once it is next page is requested. Read ahead means if I ask for the next page, you bring next 4 pages. It helps to optimize sequential access. Remember the disk hit rate is 85%. So that definitely helps. And this also locality of disk read that is into place. Finally, When the data are read from a disk file, the block IO system does some read ahead. However, writes are much more nearly asynchronous than our reads, because when you read a file, you have to read line by line. When you write to a file, you can write it doesn't matter if the system writes first line and then 10th line and then second line, it doesn't matter. But when you read, you cannot read first line and then 10th line, then second line and so on. So reads are slower than writes often. Reads has to be synchronous often. I'm not giving you a general, I'm just giving you a general idea. Reads are often asynchronous and writes are often asynchronous. So output to the disk, so whatever writing on the disk to the file system is often faster than input for large transfers when you're reading from the disk. And this counter to the intuition, because you might think the writing means you need to change the disk, read and bytes, and reads is just you are just reading it. No, reads are slower than writes simply because of the synchronous asynchronous problem. Writes the disk can do themselves. Reads, they need to be more to the user's liking. They have to do asynchronously. Okay, with this, our operating system class comes to an end. And thanks a lot for joining the class and for the lively discussion. Any questions? I know that we have like 2 minutes on this, but our file system, this is the end of the file system. And are there any questions? So if there are none, please use the MS Teams, or some of you actually mailed me, which was really, really pleasant. Actually, like it's quite pleasant actually, like, that you, so if you have any doubts, feel free to reach me, SG, any of us through MS Teams, through private messages, through emails. And if you have any doubts, we are more than happy to try to, answer those. So thanks a lot again. I'm stopping the recording. Please go over these recordings carefully, and best of luck for the exam.